all to the session for insights on transformers. This is Dr. BenChristopher, Assistant Professor, Department of Electrical and Electronics Engineering, PSL College of Engineering and Technology. So, in this presentation, we are going to see the various insights of the transformers. So, initially we are going to see what is a transformer, and next what are the constructional features of the transformer, and next we are going to see about the principles of operation which is present in the transformers, and EMF equation of transformer. Next, along with the EMF equation, next we are going to see about the importance of phasor diagram of the transformer. Next, to assess the internal parameters, we are going to see about the equivalent circuit of transformer, and next various types of transformer, that is auto transformers, tap changing transformers, and associated with this we are going to see what are the various aspects to be followed in the parallel operation of single phase transformer. Next, different types of three phase transformer connections. So, and next parallel operation of three phase transformers and squad connection of transformers. So it is a collection of various insights of transformers, just to remind what is the importance of the transformer present in the power system and various other systems. So basically, transformer, which is a static electrical device, so which is responsible to transfer electrical energy from one circuit to the another circuit, and this circuit is isolated by means of electrical connection, and it is connected magnetically. It works on the principle of electromagnetic induction. So basically, Faraday's magnetic law of induction is used in this transformer working principle, and the changes in voltage level without changing the frequency is the prime principle of working of the transformer, because if you want to step up the voltage and step down the voltage without changing the frequency of the alternating signal, we are going to use this transformers. So as I said earlier, it is electrically isolated and it is magnetically coupled. So this transformer is used in various types of applications: power transmission, distribution system, electronic devices, renewable energy systems. And coming to the next part, main parts of transformers. So there are five main parts of the transformers. Initially, the magnetic core, the primary winding, the secondary winding, insulation, the tank, and the oil, which is mainly used in the power transformer. Magnetic core. So this is a steel magnetic core present in the heart of the transformers. So the cores are primarily responsible to transfer the magnetic flux from the primary winding to the secondary winding. So as it is transferring the flux from the primary to secondary, it should have a very low reluctance path for the magnetic flux to transfer. It is basically made of laminated steels, so in which different stacks and multiple number of stacks are used to form this core. Okay, this multiple number of stacks is used to reduce the hysteresis loss and eddy current loss due to unwanted current circulation induced due to the magnetic flux by means of electromagnetic induction. So it is made up of laminated silicon steel. So this gives a good efficient performance of this transformers. Next, the primary winding. So initially, the supply, the alternating supply is given to the primary winding. So if it is a step down transformer, a high amount of voltage level is given, and if it is a step up transformer, a low level of voltage is given. And in the secondary, we are experiencing, for a step down transformer, we can experience a low amount of voltage comparing to the input, and in step up transformer we can experience a high amount of voltage comparing to the input of the primary winding. And insulation. So insulation is one of the main working part of high voltage transformers. So in low voltage, the air circulation and the air environment surrounding the transformer itself is enough to cool the transformer. But while working in a high tension and high voltage application, there is a defined part of insulation should play an important role, and it occupies nearly 50% of the cost of the transformer. So the prime element for insulation is the insulation oil, so which carries some engineering mechanisms, and the engineering mechanisms include the cooling tubes, the conservator tank, and the silica gel breather, the buckles relay, so and the oil level indicator. So all this plays a major role in insulating purpose of the transformers. So next is the tank and the oil. The oil is mainly used in high voltage transformers, is mainly used to reduce the heat generated during the working process. So during the heat generation, the oil absorbs and it expands, and the expanded oil is being raised to the conservator. So the conservator which then cools and then contracts the oil and sends to the buckles relay. So at the same time, this cooling has some air circulation inside. So this air circulation induces some amount of moisture, and there is some amount of dirt, and both the things are being reduced and filtered by means of a silica gel breather, which prime purpose is to reduce the water content at the point. Next, the principle of transformer. A transformer works on the basic principles of Faraday's law of electromagnetic induction and the mutual induction between two coils. So here there are two coils. The initial one is primary and the second one is secondary. So the primary coil has n number of turns, which is termed as NP, so primary number of turns, and secondary has secondary number of turns. So here the main thing is only the level of voltage is being adjusted between the primary and the secondary without altering the frequency. So initially when the current is given to the primary, or the voltage is applied to the primary coil, the current flows through the primary coil, and this current induces a self-induced EMF E1 across the primary winding. This induced EMF then produces the magnetic flux throughout the core and links the secondary coil, and this secondary coil produces another one, electromagnetic potential difference E2, and this E2 induces a current I2, thereby giving the terminal voltage as output. So next, the working of transformer. So transformer, as I earlier said, it works on the principle of mutual inductions. So basically only alternating current signal, okay, with proper voltage level or magnitude can be used for this transformer principles, transformer working. So if DC is used, definitely it becomes short circuit, as it is it produces constant field that cannot induce any voltages. So only AC can be used. So changing magnetic field is primary requirement for this induction. And next, the voltage transformation. The ratio of turns between primary and secondary coil determines if the voltage is stepped up or stepped down between the two electrically primary isolated circuits, that is primary and secondary, and magnetic core. The magnetic core is made up of soft iron or steel core, which is used to produce the magnetic flux, coupling both the coils, that is primary and secondary, and improving the efficiency by guided magnetic field across this core. And energy conversion. So the conversion of energy is basically attained by maintaining the constant power, because as power remains relatively constant, apart from the minor losses, the power is relatively maintained as a constant parameter in the energy conversion process. Also in this, the frequency also remains a constant. That is one of the important point of consideration in the working of transformer. And coming to the various types of transformers, first the core type transformer, and second the shell type transformer. So based on the type, based on the construction type, this classification is made. In the core type transformer, the winding surrounds a considerable part of this steel core. So in one limb of this transformer core, we are winding the primary, and in the other side we are winding the secondary. So this is used for easy cooling. The core type transformer is used for easy cooling and used in very high applications. And coming to the shell type transformer, it is surrounded by core. The windings are surrounded by the major part of the core, and it has better mechanical strength which can be used in low voltage and high current applications. And the next type of this transformer is, it is classified by means of the turns ratio. So step up transformer and the step down transformer, that is the windings present in the two limbs differs. For example, if you take the step up transformer, a low voltage is applied in the less number of turns of the primary winding, and the high voltage is attained as the output through the large number of secondary windings. And the same case is reversed in case of the step down transformer. And coming to the categorization of the types of transformer based on the power application, it is categorized into three types, that is power transformer, distribution transformer, and instrument transformer. So the power transformer are used in the transmission networks where the voltages are very much high, which is equal to around 400 kilovolt or more than this. And in the second part, it is a distribution transformer. Here we are using the distribution transformer for low voltage application near to the consumer side and near to the distribution poles. So here the voltage level is moreover very much less than the power transformer ratings, which is around 11 kilovolt. The instrument next is case is the instrument transformer. So this is primarily used in the substations, which is used to measure high voltage, current, including the current transformers and potential transformers are some of the examples of the instrument transformers, and based on the core medium. So there are two types on this. Initially, it is the iron core that we have seen, the steel laminations or the stacked lamination core, so which can be used to do high level power transfer efficiency, and it is stacked and it is laminated. And coming to the air core transformer, so here it is air is used as a core, or wooden cores are used as a core of this air core transformer. So it is highly used for high frequency applications where the communication signal has to be established. So next is the based on windings, so auto transformer and single phase and three phase transformer. So in auto transformer, there is one single winding for both primary and secondary, and they are very much smaller and more efficient, and it is used for low voltage applications. Another thing, we are using tapping to extract the different voltage levels from this auto transformer. And single phase transformer and next three phase transformer, based on the different phase of the electrical supply, we are using this single phase transformer and the three phase transformer. If you are using single phase supply as input, then you can use single phase transformer, and if you are classifying or dividing the phase by 120 degree, that is the three phase system, so we are going for the three phase transformer and based on the installation location. Okay. So there are three categories: pole mounted. As we see, our Indian electrical system is mainly overhead electrical systems. Here it forms the pole mounted transformers. So two poles are there, and it is attached by means of iron rods, and the transformer is placed right over this. And next is in cities, we are using pad mounted transformers. So most probably these are seen near substations in near cities. So pad mounted is mounted in the ground of the substation, and here it is enclosed by means of separate cabinet box, and this box protect the transformer from the rain and the moisture and different climatic conditions prevailing over it. And next is underground and submersible transformers. These underground and submersible transformers are used in highly congested cities and modern cities to replace the structure of the transformer from the view of the customers. So it is specially submerged under the ground, and they are mainly used with a good amount of cooling and good amount of air ventilation. So a separate unit is used to pump the waste air and emissions coming out of these types of transformers. So this is very safe, and cabling systems are used for this type of transformers. And coming to the mathematical part of the transformer, first we are going to discuss about the EMF equation. I am not going to derive here. So, but what is the concept why we need for EMF equation of the transformer? So let me discuss here. So the concept is when alternating current flows through the primary winding, so it produces an alternating magnetic fluxes in the core. This flux links both the windings, that is the primary and the secondary winding, and induces EMF according to the Faraday's law of magnetic induction. So Faraday's magnetic law of induction states that the induced EMF E, which is equal to the number of turns into the change in flux over the time, and the entire term is made as negative. And here E is the induced EMF, and N is the number of turns, and phi is the magnetic flux in Weber. So the EMF equation of the transformer moreover takes this concept and this derivation. E1 is equal to 4.44 into frequency into N1, that is the primary number of turns, and the phi maximum amount of flux. So here what are the things to understand is the primary EMF as well as secondary EMF is always proportional to the form factor of 1.11, and always proportional to the frequency, and always proportional to the maximum number of the number of turns, and always proportional to the maximum flux induced across the core of the transformer. So everything is directly proportional. This gives the total amount of induced EMF across the transformer. So the voltage ratio is given by E2 is the induced voltage across the primary winding, and across the secondary winding, and E1 is the induced voltage across the primary winding, which is always equal to the number of turns of the secondary divided by the number of turns of the primary. And this equation is called as the turns ratio of the transformer. So meaning is, if the frequency decreases, the flux increases, causes the core to saturate and overheat. And coming to the equivalent circuit of the transformer, what is the need for equivalent circuit of the transformer is, the transformer which we speak till now is not ideal. It is ideal and it is not practical, because all the transformer and the windings have winding resistance. Also, when the flux is induced in the core, this flux then has the tendency to leak from the core to the air surrounding or the environment surrounding it. Okay, this will cause a leakage flux. And coming to the core, when it transfers the current field flux, magnetic flux to the secondary, it always has some loss. Okay. So in order to assess all these practical parameters, the transformer, that is the ideal transformer, requires the equivalent circuit analysis. So the main element here represented is the primary resistance, which is responsible for the copper loss in the primary winding, and the secondary resistance, which is responsible for the copper loss in the secondary winding, and leakage reactance. Okay, this is both primary and secondary leakage flux considered, okay, during the operation of the transformer. And next to the core loss resistance, so this is mainly used to address the hysteresis and eddy current loss of the transformer. Next, the magnetizing reactance. So this is due to the magnetizing current that is induced across the transformers. So this is the equivalent circuit of the transformer. So this represents the core loss and represent the loss due to the reactance. So similarly, so magnetizing reactance and the core loss resistance. So there is a mutual induction between the primary and the secondary winding, and here secondary leakage reactance, and here it is the secondary copper loss across the transformers. So the practical importance of studying the equivalent circuit of the transformer is, so it is basically used to study the voltage regulation and calculate the value of voltage regulations. So transformers has a different amount of load, and this load is one of the prime factor to decide the output load current. And if the voltage given is constant and the load current varies, so definitely it will create a burden on the secondary transformer, and this burden has to be avoided, okay, by means of voltage regulation. So, and again it is used for efficiency analysis. The basis of transformer testing, that is open circuit and short circuit test, can be assessed using this equivalent circuit of the transformers. The phasor diagram of transformer, and the phasor diagram is the graphical representation showing the phase relationship between the voltages, currents, and the flux induced in the transformer. It is important because it helps to understand the various behavior of the transformer under different loads, and it is used to analyze the voltage regulation. It shows phase relationship between the current and voltages. So the types of phasor diagrams are no load phasor diagram, loaded transformer phasor diagram. So under the loaded transformer phasor diagram, we are having three different things, that is lagging power factor load in case of inductive load, leading power factor load in the sense of capacitive load, and unity power factor load in the sense of resistive load. So conditions at no load, secondary winding should be open and only a small amount of current is flowing in the primary, and primary winding carries a small current I0 called no load current, which is the 2 to 10% of the rated current of the transformers. There are two components, that is a magnetizing current IM, and there is a core loss current IC. So I0 is given by IM plus IC. And transformer and the lagging power factor, when the load is connected, the secondary current I2 flows, so I2 flows, and this current produces a demagnetizing flux, and this flux has the effect of demagnetization and turns around the origin of the transformer, and it rotates and it induces a E2, and which is already equal to the E1. And the transformer reaction, the primary draws additional current I2 to balance the flux, and voltage relations is given by V1 is equal to E1 plus I1 R1 plus J I1 X1. V2 is equal to E2 minus I2 R2 minus J I2 X2. So here E1 and E2 lag the flux by 90 degree. Flux is almost constant for both no load and full load condition, and the load affects the current and not the flux. The flux is not affected in the core, and the current flowing through the secondary winding is being affected, and this induces an impact in the primary winding, and which also draws the most high quantity of supply from the primary side. And the transformer balance principle is given that the primary current is automatically adjusted so that N1 I1 is equal to N2 I2. Even the load changes, the core flux remains nearly constant, and the transformer behaves like a constant flux machine. And coming to the auto transformer, an auto transformer is a transformer with a single continuous winding acting as both primary and secondary. So the key idea of this is, unlike a conventional transformer, the primary and secondary are not electrically isolated. So in the conventional transformer, the primary winding and the secondary winding is isolated, but in case of the auto transformer, it is not isolated. So it is basically used for voltage regulation, starting of the induction motor, power system interconnections, and variable AC supply used in the laboratories. So the constructional features of this auto transformer is, it consists of laminated magnetic core and single winding with multiple number of taps, and both input and output terminal in which output terminal is connected with the load. The working principle is when the alternating current supply across the primary winding, the current flows through this winding. So the magnetic flux itself produced in the core and EMF induced along the winding. So using different tappings, we can extract the EMF induced along the winding to the load and thereby attaining the output voltage to the auto transformer. So one of the biggest advantage of this auto transformer is the requirement of the copper winding used in the transformer is very much less, and it also, as the copper is very much less, it exhibits a smaller size, and when it is in a smaller size it exhibits a low amount of weight, and this also produces a higher amount of efficiency due to reduction in losses and a good amount of voltage regulation. Continuous voltage regulation can be achieved in this auto transformer, and also the size and weight and the amount of copper used in this auto transformer is low, which can yield the lower cost. And it also has disadvantage, as in case of any fault, it is more prone and to the faulty conditions, as it has no electrical isolation, and there is high amount of short circuit current can be induced, and not suitable for very large voltage ratio, as it is limited with the less number of turns. And coming to the practical application, it can be used for starting of the induction motor, attaining various quantity of voltage levels across the secondary winding, voltage booster in transmission lines, and interconnection of electrical system with close voltage levels. So the technical insight is power transfer occurs in two ways. First, inductively coupled power and conductively transferred power. So this is one of the phenomenal feature of the auto transformer. Because of this, the transformers can reach efficiencies up to 90%. And next, after the after the auto transformer is the tap changing transformer. The tap changing transformers adjust the voltage levels by means of number of taps. There are two main types, that is OLTC, offload offload tap changer, and on-load tap changer. So in offload tap changing principle, the tap position changed when transformer is de-energized. When the transformer is disconnected from the load and there is no load current, we can change the tap position, thereby attaining the required amount of voltage. And it is mainly used in distribution transformer, and the construction is very much simple. But this is replaced by on-load tap changer, as to satisfy the reliable feature of the power supply to the customer. So we are using on-load tap changer. In this, the tap position changed while the transformer is kept on and being operating, and used in the power transformer in transmission system. It allows continuous voltage regulation. So the various components of OLTC is tap winding, selector switch, diverter switch, transistor resistor or reactor. So here the tap winding is the winding, various winding levels, and in which the tap is fixed. The selector switch is the switch that is that makes the OLTC to works offline. Okay, even it is online, it works off without connecting, it works online, but this is not engaged lively, and this is directly given to the transition resistance. So suddenly, and in the selector switch there is no formation of arc, because as the load current changes, as we are switching from one voltage level to the another voltage level, definitely there is a spark or arc coming around this selector switch. So this can be avoided by means of disconnection of the selector switch in relation with the diverter switch. So as the selector switch selects the required amount of load resistance or load quantities, so the diverter switch suddenly trips the selector switch, and thereby it can come to the plate to handle this resistance, and as a result there is a formation of arc. This arc can be limited or captured by means of the transformer oil, which can be filtered by means of the silica gel breather. So here the working principle is the selector switch chooses the next tap position, the diverter switch transfers the current to the new tap, the transition resistance prevent short circuit between the taps. This allows the voltage change without interrupting the load. So the main advantage is maintain constant voltage at the load side, improves voltage regulation in the power transformer, and it is highly essential for long transmission line. And the major applications of this type tap changing transformers are the power transmission networks and substation transformers, grid voltage control. All of them uses the tap changing transformer, which is basically now it is OLDC. So the typical tap range is can be considered as plus or minus 10% of the rated voltage. So parallel operation of single phase transformer. So the parallel operation of single phase transformer means connecting two or more transformers to a common load so that they have to share the load current between them. So this parallel operation is used to increase the power capacity and to improve the overall system reliability and provide flexibility during the maintenance of the transformers and allow future load expansion. The basic concept of parallel operating two transformers, two single phase transformer is, so instead of installing one large transformer, depending upon the load condition, that is various load condition, multiple smaller transformers are connected in parallel supply to deliver the same load for the same required amount of current. And there are some conditions of this parallel operation. So of single phase transformers, it has to have a same voltage ratio, it has to have a same polarity, it has to have similar amount of frequency, and it should exhibit a same impedance value. So advantages, it increases the system capacity, it increases the better reliability of the system, it is easy for the maintenance purpose, and higher amount of efficiency can be attained used for different amount of loads. So parallel operating of single phase transformer, here 200 kilowatt ampere transformers connected in parallel can supply a total capacity of 200 kVA load. So and similar to this case, single phase transformer, three phase transformer can also be parallelly operated. So the same advantage and same requirement of the single phase transformer. So here allowing provide another one advantage is here is requirement is it provide flexibility for a very good load growth. So that is one of the prime importance of this three phase transformer, and the conditions are the same, but one thing is being added, that is it should exhibit same amount of voltage, same polarity, same impedance, everything, but other three are very much important. As we are working on three phase transformer, the phase angle is somewhat different from the single phase transformer. Okay, the supply has three phases, and three phases are 120 degree apart by means of circular and by means of sinusoidal. So the phase sequence of both R, Y, B or the three phases A, B, C should be in sequence. If it is not, there will be an occurrence of short circuit between the various windings of the transformers. So also it should have same phase angle displacement. So it should have same vector. If one position is being cyclic, another is non-cyclic, that should not be accepted. That is, for example, if one is turning anti-clockwise, another is going clockwise, it is not accepted here. It should have the same amount of phase angle displacement. And as I said earlier, it is for a single phase transformer, how the per unit impedance is important. Here also the per unit impedance is important for parallel operating three phase transformers. So load sharing. So load shared by the three phase transformers is inversely proportional to the impedance, and the transformer with lower impedance carries more load. So if conditions are not met for parallel operation, that transformer can experience a different phenomenal disadvantages. So that is, it induces a circulating current which surplaces between both the transformers. So this is one of the similar thing what happens in the eddy current problem. So the circulating current between transformer 1 and transformer 2 makes the transformer to be overheated, and here there is another problem of unequal load sharing, so that the burden is carried by the lower impedance transformer as a more one, and overheating of one transformer, thereby reducing the efficiency. And Scott connection of transformer, this is one of the different, and most of the thing now wherever we require two phase power supply. So by using two single phase transformers, we are using to extract a two-phase power supply. So here transformer used is main transformer and a teaser transformer. So this is the connection of this Scott connection of transformer. The main transformer connected across the two phases of the three-phase supply. The teaser transformer primary is connected to the third phase, that is R phase, and the midpoint of the main transformer. This midpoint, how it is derived is, it is root 3 by 2 NP, that is of the main transformer. The number is clearly defined as fraction as 0.866 into n, where n is the number of turns of the main transformers. So without this number, we can't able to get the Scott connection of a transformer, and also this will yield a problem of circulating current between the two windings of the transformer, and this number should ensure a balanced two-phase output out of this Scott connections. So the advantages is the balanced loading of three-phase system, efficient three-phase to two-phase conversion, the smoother power transfer. Key characteristics are output phases are 90% or 90-degree apart, so both transformers carry equal amount of kVA load. The voltage transformation follow transformer turns ratio, and the Scott connection is mainly used where two-phase loads exist but only three-phase supply is available.